By the end of the Permian, Earth was no longer a balanced world. It was a system under strain. The continents had fused into Pangea, a landmass so vast that its interior became isolated from oceanic moisture. Without that stabilizing influence, climate patterns grew increasingly erratic. Prolonged aridity dominated much of the landscape, interrupted only by brief and often unpredictable wet periods. Atmospheric oxygen had declined from earlier peaks in the Carboniferous. Not catastrophically, but enough to place subtle limits on large, energy-demanding animals. Beyond the coasts, the global ocean told a similar story. In the aftermath of the Capetanian extinction, marine ecosystems had not fully recovered. Reef-building organisms declined, and complex food webs gave way to simpler, less resilient structures. Panthalassa remained vast, but it was no longer robust. As marine systems weakened, evolutionary pressure did not disappear. It relocated. On land, survival demanded new solutions. Water retention, behavioral flexibility, and tolerance to extremes. These were not optional traits, but prerequisites. The most intense evolutionary pressures on Earth were no longer found in the oceans, but across the dry, unstable expanses of the land itself. Out of this shifting world, a new kind of predator began to take shape. Not the sprawling, low-slung reptiles that had dominated earlier landscapes, but something more efficient, more deliberate, the gorgonopsids. Biologically, they belonged to therapsids lineage, a group that would eventually give rise to mammals. And in their anatomy, we can already see that transition beginning. Their limbs were positioned beneath the body in what paleontologists call a parasagittal posture. It allowed for more efficient movement, reducing the side-to-side energy loss seen in earlier reptiles. Over long distances, that efficiency mattered. It meant these animals could move farther, track longer, and conserve energy in an environment where resources were often scarce. Their skulls tell an equally important story. Long, narrow, and built for targeting rather than crushing. But the most striking feature was the pair of elongated canines. Saber-like teeth could extend over 4 to 6 inches. These were not tools for brute force. They were precise instruments. The bite itself was not exceptionally strong by modern standards. In some specimens, faint serrations on the scale of fractions of an inch suggest an edge adapted to initiate and extend cuts through soft tissue. The strategy was different. A controlled strike, a well-placed bite, then withdrawal. Rather than grappling with prey, they likely inflicted deep wounds and allowed blood loss and shock to do the work. It is a method that minimizes risk, especially important in a world where injury could mean death. There is no clear evidence that they hunted in coordinated groups, so each individual needed to succeed alone. This is what sets them apart. They were not the strongest predators of their time, but they may have been among the most refined. In a landscape where energy was limited and conditions were unstable, success did not come from power alone. It came from efficiency, from precision, from doing exactly what was needed and no more. In that sense, gorgonopsids represent something new in the history of life on land. Not just predators, but specialists. Among the gorgonopsids, one predator stands apart not because it dominated everything around it, but because it fit its world with unusual precision. The Inostrancevia. It lived in the northern regions of Pangaea, where ecosystems were unstable and often fragmented. Seasonal temperature swings, shifting river systems, and uneven prey distribution meant that encounters were unpredictable. In such conditions, success depended less on confrontation and more on efficiency. Inostrancevia reached lengths of around 10 to 11.5 feet, placing it among the largest terrestrial predators of its time. Its skull could exceed 18 inches, yet remained relatively narrow, reducing resistance during a strike. The canines, extending up to 5 to 6 inches, were not only long, but thin and blade-like, with cross-sections optimized for penetration rather than durability. But the more revealing detail lies in how those teeth were used. Recent functional interpretations suggest that stress concentration during a bite was localized toward the tips of the canines, meaning the initial puncture required relatively little force. The goal was not to clamp down, but to breach tissue quickly, then withdraw before resistance built up. The neck structure supports this. The cervical vertebrae show adaptations for controlled flexibility, allowing slight rotational movement during retraction. This would convert a simple bite into a cutting motion, increasing wound severity without prolonged contact. Its locomotion reflects the same pattern. Limb proportions indicate a stride suited for steady, energy-efficient movement, rather than explosive sprinting. This suggests a hunting behavior centered on tracking and positioning, not chasing. Closing distance gradually, selecting the right moment and committing only when success was likely. There is also evidence of low tooth replacement frequency compared to later therapsids, implying that each strike carried a cost. Damaging a canine was not trivial. That alone reinforces the idea of careful, calculated engagement. And that is the key. Inostrancevia was not the strongest predator in its environment. It did not rely on overpowering prey. It succeeded because it reduced risk, conserved energy, and matched its strategy to the conditions around it. In a world where resources were uncertain and mistakes could not be afforded, that made all the difference. Not the most powerful, but perhaps the most precisely adapted. Far to the south, in what is now the Karoo Basin of South Africa, a different version of the same predator was taking shape, the Rubidgea atrox. Closely related to Inostrancevia, Rubidgea belonged to the same evolutionary lineage. But its anatomy tells a very different story, not of efficiency over distance, but of control at close range. Rubidgea was slightly shorter on average, reaching around 8 to 10 feet meters in length, but it was more heavily built. Its torso was compact, its limbs robust, and its center of mass lower, features that suggest stability rather than endurance. This was not a predator designed to track prey across open terrain. It was built to engage and hold. The skull is where the difference becomes most apparent. Compared to the narrower skull of Inostrancevia rubidgea's, skull was broader and structurally reinforced with thickened bone in regions that would experience high mechanical stress. In some specimens, the cranial roof shows evidence of bone thickening and surface rugosity features, often associated with resistance to impact or strain during struggle. The canines remained long, typically in the range of 10 to 12 centimeters, but they were supported by a more robust jaw architecture. Finite element studies of related Rubidgea skulls suggest that force distribution was better suited to sustained contact rather than rapid withdrawal. This changes the entire hunting dynamic. Where Inostrancevia likely struck and disengaged, Rubidgea appears to have done the opposite. An ambush, a forward lunge, contact maintained. Its jaws could grip, stabilize, and then apply cutting force. The neck and shoulder musculature inferred from attachment sites indicates strong downward and lateral control, useful not just for biting, but for manipulating struggling prey. Its environment helps explain this shift. The southern Permian ecosystems, particularly in the Karoo region, supported dense populations of large herbivores, such as dicynodonts. In such settings, encounters were more frequent, and competition between predators was likely more direct. Under those conditions, the ability to secure and dominate prey quickly would offer a clear advantage. Rubidgea reflects that pressure. Not faster, not more precise, but more physically assertive. And this is where the comparison becomes meaningful. Two predators, one lineage, yet shaped by different environments into two distinct strategies. Inostrancevia minimized risk through precision. Rubidgea managed risk through control. Neither is inherently superior. Both are solutions. Together, they reveal something fundamental about evolution in the late Permian. It does not move toward a single ideal form. It responds quietly, consistently to the conditions that define survival. Not every Permian predator grew larger or more specialized. Alongside the Gorgonopsids, another lineage followed a different path entirely, the Therocephalians. They were generally smaller, most measuring between 3 to 6.5 feet in length, but their proportions reveal a shift in strategy. Their skulls were relatively large, often making up over a quarter of total body length, with jaw joints positioned to allow rapid opening and closing. This is not a design for sustained force. It is a design for speed. Among them, one predator stands out, the Mascarinus. Mascarinus approached the upper size limits of the group, yet retained the same underlying advantages. Its skull was broad and reinforced, but unlike Gorgonopsids, its teeth were conical and robust, better suited for gripping and puncturing than slicing. This suggests a different kind of interaction with prey, less about precision wounds, more about securing and subduing quickly through repeated bites. Its postcranial skeleton indicates greater flexibility. Limb joints allowed a wider range of motion, supporting quick directional changes. In several related species, anatomical traits such as limb proportions and tail structure suggest semi-aquatic capabilities, allowing them to exploit riverbanks, shallow lakes, and transitional environments where larger predators were less efficient. There is also a more speculative detail. Some Therocephalian fossils show grooved teeth and internal channels, features that in modern animals are often associated with venom delivery. If accurate, this would represent one of the earliest uses of venom among terrestrial vertebrates. However, this remains unconfirmed, as no soft tissue or chemical evidence has been preserved. It is a hypothesis plausible, but not yet proven. Even without venom, the pattern is clear. These animals did not compete by becoming the dominant force in a single niche. They diversified. Different prey, different habitats, different methods. And that is the larger insight. While gorgonopsids refined two powerful strategies, precision and control, therocephalians explored alternatives: agility, adaptability, and ecological range. By the late Permian, predation was no longer confined to a single space. It existed everywhere. On land, large therapsids, gorgonopsids, and advanced therocephalians occupied the role of dominant hunters capable of targeting medium to large herbivores. But the pressure did not end there. Along river margins and floodplains, a different set of predators waited. Semi-aquatic reptiles, such as early archosauriform relatives, including forms similar to proterosuchids, occupied the boundary between land and water. With elongated skulls and conical teeth, they were adapted for sudden upward strikes, seizing prey that came too close to the shoreline. In the water itself, large amphibians, particularly members of the Rhinosuchidae, filled the role of ambush predators. Some species reached lengths of 10 to 13 feet, with broad, flattened skulls and powerful tails. Their sensory positioning suggests they could remain nearly submerged, detecting movement above the surface before launching a rapid attack. What emerges is not a hierarchy, but a network. Each ecological niche, open ground, river edge, shallow water, was occupied by a predator adapted to that specific environment. There were no unused spaces, no safe transitions between habitats. For herbivores, this changed the rules entirely. Movement between feeding grounds, access to water, even moments of rest, each carried risk. Survival was no longer determined solely by size or strength, but by awareness, timing, and behavior. Because in this world, danger was not concentrated. It was distributed. Survival was no longer about strength. It was about avoiding attention. For a long time, the system worked. Predators adapted to scarcity. Prey adapted to pressure. The balance was harsh, but it held. Then, the baseline began to change. In what is now Siberia, the Siberian Traps eruptions released sustained volumes of volcanic gases, especially carbon dioxide, over extended timescales. This did not create a single disaster. It shifted the conditions life depended on. Temperatures rose, not uniformly, but enough to disrupt already fragile ecosystems. At the same time, atmospheric oxygen declined to levels estimated around 12 to 16%, narrowing the limits for large active animals. The oceans followed a similar trend. Warmer water retained less oxygen and circulation weakened. Over time, large ocean became oxygen poor, a process known as anoxia. Marine ecosystems simplified, then collapsed in many regions. This transition marks the Permian-Triassic extinction event. It was not sudden, it was cumulative, and that made it decisive. Highly specialized predators like gorgonopsids and advanced therocephalians were among the most vulnerable. As prey networks broke down, their strategies no longer worked. They did not disappear because they were outcompeted. They disappeared because the system itself changed. These creatures are often described as monsters, but that is not what they were. Gorgonopsids therocephalians. These animals were not excesses of evolution. They were responses to it. Each feature, from elongated canines to reinforced skulls, reflects a specific pressure, a specific constraint, a specific environment. They were not designed to dominate everything. They were shaped to function within a system, and for a time, they did exactly that. They did not fail. The world they were built for simply disappeared. And when it did, evolution did what it always does. It started again. And if you're interested in how those new worlds took shape, how life rebuilt itself from near collapse, subscribe to our channel.